In this section, we'll be looking at the graphs of the remaining trig functions: cosecant, secant, tangent, and cotangent. In the graphs down below, we have the graph of sine x and cosine x from the interval 0 to 2 pi. We'll see in a bit how to derive the graphs of cosecant and secant from the graphs of sine x and cosine x. Beforehand, though, let's go ahead and sketch what it's going to look like. For cosecant x, our graph will look like the following, and for secant x, our graph will look like the following. Recall now that sine and cosine have period 2 pi. This means that if we have the interval between 0 and 2 pi, the graph is going to repeat this pattern from negative infinity to positive infinity. We'll be using the fact that trig functions are periodic functions, and more specifically, because cosecant and secant are reciprocals of sine and cosine, they also have a period of 2 pi. Writing this symbolically, this is equivalent to saying cosecant evaluated at x plus 2 pi is equal to cosecant x, and secant evaluated at x plus 2 pi is equal to secant x. And I just noticed that cosecant is missing a part of the graph, so let me go ahead and fill that in. This is the remaining part of our cosecant graph that we were missing. We'll now derive the graph of cosecant x from sine x. Recall first that cosecant x is equal to the reciprocal of sine x. This implies that when sine x is equal to 0, cosecant x is undefined. Sine x is 0 when our angle theta is equal to some multiple of pi. Therefore, the graph cosecant x is undefined when we plug in some multiple of pi. In fact, what we're going to have is cosecant has vertical asymptotes at x is equal to multiples of pi. We'll restrict again the picture to be on the interval from 0 to 2 pi, but then extend it. So first, let's go ahead and draw vertical asymptotes. Now, when sine x is equal to 1, cosecant x will be equal to 1, which means that cosecant x has a value of 1 when x is equal to pi divided by 2, and cosecant x has a value of negative 1 when x is equal to 3 pi divided by 2. Now from the remainder of the graph, we need to look at the graph of sine x. Now down below, again we have our graph of sine x, and as the x values approach 0 from the left-hand side, then our y values are approaching 0. This means in our cosecant graph, since we have the reciprocal relation, that as x approaches 0 on cosecant, then our y values are approaching infinity. And this is because as we put in smaller numbers into 1 over sine x, our numbers grow exponentially large. Now again, if we look at the graph of sine x, and we approach pi from this side over here, then again, our y values are going off to 0, which means that as we approach pi on our cosecant graph, our y values are approaching infinity. Again, this is because if we plug in small values into 1 over sine x, they get exponentially large. Again, if we approach pi from the left-hand side on our graph sine x, we're still approaching 0, but this time our numbers are negative numbers that approach 0. So that means that as we approach pi from the right-hand side of our cosecant graph, then our y values are getting exponentially negative. And in the last step, as we approach 2 pi, our sine values are becoming again closer to 0, but from the negative direction. And so again, in our cosecant graph, we're growing exponentially negative. Since the function cosecant is periodic, we can just go ahead and repeat this graph. And this is the graph of cosecant x. Now let's go ahead and look at the graph of secant x. Secant x is the negative reciprocal of cosine x. Therefore, when cosecant is equal to 0, secant is undefined. Cosine x is equal to 0 at pi divided by 2 and 3 pi divided by 2 and 2 pi multiples of these numbers. So our secant x is going to have vertical asymptotes at the following x values. Again, we're going to restrict our picture to be between 0 and 2 pi, and since our function is periodic, we can extend this from negative infinity to infinity. When cosine is equal to 1, secant x is equal to 1. And this occurs when x is equal to 0. And when cosine is equal to negative 1, secant x is equal to negative 1. This occurs at x is equal to pi. Oh, I forgot the point. When x is equal to 2 pi, we also have that secant x is positive 1. To derive the remainder of the graph, we're going to look again qualitatively at cosine x. Again, our secant x has a reciprocal relation with cosine x. So when cosine x gets very small, secant x gets very large. So on the graph of cosine x, as we approach pi divided by 2 from the right-hand side, then the y values are going to 0. This means that on the secant graph, our y values are getting infinitely large. On our cosine graph, when we approach pi divided by 2 from the left-hand side, again, our y values are approaching 0, but now they're all negative. So on our secant graph, as we approach pi divided by 2 from the left, our y values are getting extremely large again, except this time in the negative direction. Now, as we approach 3 pi divided by 2 on the cosine graph from the left-hand side, again, our y values are approaching 0, but they're all negative. So this means that on our secant graph, as we approach 3 pi divided by 2 from the left-hand side, our y values are growing extremely large, but again, they're growing in the negative direction. And for the last bit, as we approach 3 pi divided by 2 from the right-hand side, our y values is still going off to 0, but this time all the numbers are positive numbers. So on our secant graph, as we approach 3 pi divided by 0, our number is becoming extremely large, but they're all positive numbers. So our graph looks something like this. Since secant x is periodic, we can go ahead and extend this picture for the entire graph. Like sine and cosine, cosecant and secant have transformations that affect them in predictable ways. The standard transformations on these functions are given by the following equations. Again, this form tells us quite a bit about the transformations that affect these graphs. A is no longer called the amplitude, but it still affects our graphs by vertically stretching them. K determines the period of our graph, and so is a horizontal stretch or compression, and H is our horizontal shift, where we have that if the number H is greater than 0, then we shift left, and if H is less than 0, we shift right. For example, sine of x minus 3, we're going to shift our graph to the right by 3 units, and sine of x plus 3, we're going to shift our graph left by 3 units.